My name is Edoardo Vacchi. Thanks for letting me do this presentation here. It's exciting. I wish I were there. uh, this is going to be a very engineering-oriented presentation. I'm going to tell you a little bit about Chicory and a little bit about my company, in case you're not familiar with it. Um, yeah, also a little bit about myself, but uh, long story short, I've worked on wazero for a couple of years, a year and a half at Tetrate. Tetrate is the company that started wazero, it's maintaining wazero. I'm still contributing to wazero, but I moved to Dylibso. And Dylibso is the company behind Chicory, although we have quite a few contributors and one large contributor and maintainer at Red Hat. In case you're not familiar with Dylibso, one of the most famous projects that we have, I would say, it's called Xtism. Xtism is a framework to develop plugins and extensions. It's laid on top of core Wasm. We have implementation of our SDK for several different languages. It allows you to plug inside your application Wasm runtime, abstract away the details about its own API. And then on the other hand, we have PDK plugin development kits for a few different languages that allow you to write using our interface abstracted away for any of these languages. So our API is implemented more or less the same across a lot of different runtimes. And I'm going to focus on, obviously, Chicory and a little bit of wazero today. Before I start, I wanted also to tell you about a project that we launched a few weeks ago. It's called mancp.run. It's related to AI. Allows you to write agents, and it's all based on Wasm and Xtism and a lot of our tooling. So in case you're interested, it's fun to play with. And basically, all of the uh, interfaces that are made available, tools that are made available to the AI are written using Wasm. So long story short, Wasm lets your users write software extensions using their favorite language and then run it in a sandbox environment. We already all know that. Um, Last year at Wasm.io, we introduced this concept of language native runtimes, I would say for lack of a better term. Language native runtime is a runtime that is written in the host language. You might say, yeah, that's all languages. That's all runtimes, right? But we especially mean managed languages in particular. The inspiration came from wazero. Wazero is a Go runtime written in Go, and Chicory is a runtime for the JVM written in Java. But why is that? So there's a bunch of different reasons why Go and Java are different, but there are a few reasons why they're similar. So Go and Java are definitely different. It could be more different. Go compiles to native executables, Java compiles to bytecode. Go, you cross-compile, you create self-contained statically linked binaries, and libraries that share the source. On the other hand, on Java, you have a bytecode target, much like Wasm, obviously. You have a multi-platform runtime and you port the runtime usually. You have dynamic linking because libraries are shared as binary artifacts and load dynamically and link dynamically at runtime. To the point that dynamic linking, some people have to me, the dynamic linking is kind of a defining feature of the JVM for some people. In this talk by Dan, I think we are showing, he has shown as a regular application, a Java application that usually comes with some framework, before it actually reaches the main entry point with the code that you wrote as a developer for your application, it has to go through a bunch of class loaders that grow in number as you go further in the process of initializing. And these load a bunch of classes and do a bunch of static initialization. They run some initialization code. So if you think of if you're not familiar enough with class files, and you can think of them like Wasm modules, and class loaders are just a component of JVM that does the loading dynamically on the fly upon request of those classes. And you can implement your own, or you can just look on the disk or whatever. All right, so that's how the JVM works. Now, why am I comparing Go wazero to Chicory? And why am I saying that Go and Java, after all, are not so different. Well, when it comes to linking against native code, all managed runtimes are alike. They have to deal with a foreign function interface, and in that foreign function interface, you can call it C types, you can call it libffi, you can call it JNI in the case of Java, Java Native Interface, or in Go, it's usually referred to as CGO. But more or less is the same case everywhere. You have to operate under the assumptions that you're working with native code, and with native code, they make the rules. What are those rules? So when it comes to limitation, J and CGO are kind of similar, and that's where I would say the JVM and Go are the most alike. So what are these rules? So the rules are that you cannot really assume anything about what's happening in that native code. You can't assume that it will play nicely with your runtime, with your Go routines, with your virtual threads, or with your garbage collector. Besides, you also have portability issues, like you can no longer compile once and run everywhere in Java, because now you're relying on a native binary that might not be available for all the platforms that you need. You have definitely tooling issues because you can no longer debug using your traditional Java debugger or Go debugger or profilers or coverage or fuzzing, whatever. So essentially, that's a black box. And you might also have performance issues. You might have safety issues. We all know probably all of that. Now, why then implement Wasm runtime using that language, like the Go language or the Java language? Well, the point is, you are no longer crossing the FFI boundary. You are just bringing this Wasm implementation using the language that you're using, so you're not crossing any boundary, and it will play nicely with your runtime. It will just work the way you expect. It's just like bringing in another library in your code base. So the goal here is not to have state-of-the-art performance. We have to, make some trade-offs here. But sometimes, depending on the workload, crossing the FFI boundary might be even cost more than just bringing this kind of libraries instead. So wazero is a Go runtime for Wasm. It implements an interpreter, and obviously the interpreter runs everywhere the Go compiler compiles code, is able to target that platform. And wazero also, however, implements a sort of just-in-time compiler, and I want to be super precise here, ahead of time, load time compiler for Wasm. And it's kind of unique, I would say, as a Go library, because it generates this code on the fly that jumps through some, dark magic with jumps and, assembly, jumps into the generated code on the fly. It's just a regular just-in-time compiler. You would normally do it with any other language, but doing it in Go, it's kind of, unique. So it supports MD64, ARM64, and all major operating systems. Now, Chicory is obviously different. It's first of all, it runs on Java on the JVM, and the interpreter being written in Java runs everywhere Java runs. So that includes Android. Oops, that includes Android. And Chicory implements an ahead-of-time load time Java bytecode translator for Wasm. So we're not compiling native code here. We are generating bytecode. Speaking of Android, this is a demo for mcp.run. It's running Chicory on Android in interpreted mode. And while you might think this would be pretty slow, because most of what these tools do is actually interacting with an external system doing I/O, it's kind of fast. So it surprisingly works pretty well. And the interpreter passes essentially all of the tests for the Wasm test suite, even for Android. We did this, verified this a few days ago. So how does function compilation works? Well, for wazero, usually decode the module, you validate it as you would usually do, and then depending if you're interpreting or compiling, you have two different pipelines. In the case of the interpreter, that compiles to an internal representation, and essentially is just using unstructured control flow, and that for the rest is just similar to Wasm, just reusing a bunch of opcodes, fewer opcodes for simplicity. While for the compiler, we have a different pipeline, multi-stage pipeline to produce optimized code. Now let's talk about Chicory. So the interpreter for Chicory is relatively simple. It's actually fairly one-on-one with Wasm bytecode. The goal was to be very readable, and it is very readable. It's very easy to follow and to hack. It's a code base that's really easy to play with, even if you're not especially familiar with interpreters or with Wasm. And obviously, it's portable to any JVM or Wasm or Java runtime. Now, the things get interesting with the AOT compiler. The AOT compiler is actually started as a contribution as an external contributor, which is pretty cool. It translates Wasm bytecode to Java bytecode, as I mentioned. It works online at runtime, doing something that it's actually pretty common for Java libraries, that is generating advanced Java libraries, generating bytecode dynamically and then loading it dynamically through class loading, which is the process that I mentioned earlier. Or offline, that is essentially there's a Maven plugin, there's a build tool plugin that generates the code at build time, creates these class files, these modules at build time, and then they're loaded just like any regular class file. And then for the JVM, there's pretty much no difference with any other. Now, I went a bunch of places trying to convince people that Wasm is not the same as a JVM, and now the boundary kind of becomes thinner and thinner. You probably already know that for arithmetic, JVM bytecode and Wasm bytecode are pretty much alike. The main thing where they differ is control flow. We have unstructured control flow on the JVM, whereas on Wasm, as we know, we have structured control flow. So essentially, when it comes to translating the Java bytecode, the Wasm bytecode into Java bytecode, the process is, well, of course, parsing and validating the module, then instantiating what we have called an instance from the Wasm module that now we have. Well, we called it an instance. It's called an instance, but it's called an instance also in the Java code. And then we have, well, we pass this machine factory, that it's an interpreter factory. In the case, it's an interpreter, or an AOT machine factory if it's in the AOT mode. We are Java developers. We love our patterns. What happens for the AOT machine factory is that module is translated on the fly, as I mentioned already, into Java bytecode, and then that bytecode is executed. And the process for doing this translation is pretty lightweight. Besides some light type checking that we do in order to make sure that we're using the JVM stack properly, then we just rewrite a control flow. And then that's pretty much all that happens. We generate a bunch of classes, especially we generate classes that implement some specific interfaces that in case of the interpreter are implemented by the interpreter, but in case of the compiler are interpreted by literally the translation of the module, so that it's essentially transparent to the way internally the rest of the framework works. Yeah, well, this doesn't deserve a lot of talking, but one thing that I wanted to show here is that besides control flow analysis, for most of the other opcodes, we just do a very light type checking procedure for the stack. And what's more interesting is that we can reuse a lot of the code that we have implemented for the interpreter. The nice thing about the JVM is that we can assume that a lot of the calls, the functions that implement the opcodes here that are invoked directly from the interpreter can be also invoked directly from the code that we generate, because the just-in-time compiler will inline these calls most likely, because they're very small methods. So we don't have to do the copy of the bytecode ourselves. That will happen essentially at runtime automatically in native code. So when you want to invoke a function, you just instantiate a class and you invoke the methods through some provided interface, and that's pretty much how it works. It doesn't involve any fancy jumps around and any fancy trampolines, and it wouldn't actually happen in Wazero. Okay, I also wanted to show you some promising results. They are very promising because honestly, we didn't spend a lot of time optimizing specifically the code that we generated, besides some a few things that we did. But so in case you're not familiar with GraalVM and Truffle, I mean, they've been mentioned already, but I just wanted to give a quick refresher so that we know we're on the same page. So GraalVM is sort of an umbrella project, and Truffle is the framework to implement dynamic languages. And they're implemented as interpreter using a specialized API that the GraalJIT is able to optimize. So you get great performance, state-of-the-art performance for the JavaScript implementation, great performance for Ruby, for Python, for R. And there's also a Wasm implementation called Graal Wasm that was initially, it's still shipping as part of JavaScript, but you can also use standalone. GraalJIT used to ship only in the GraalVM flavor of the JDK distribution, call it as you want. It's also available now behind a flag in the Oracle version of the OpenJDK. And there's also work in progress to be distributed separately. So here's a few diagram, very early stage results. So, but we wanted to publish them in December. We actually collaborated with Oracle to get these numbers. So it's not, we all know, they all know that there are these results. So the Chicory interpreter, when running on Graal, the commercial version of Graal, the community version of Graal, the open source version, or Temurin, which is essentially OpenJDK compiled and validated by community process, and Temurin using GraalJIT, which is a special. It's still Temurin, and it's bringing GraalJIT through some fancy magic commands and incantations. So the Chicory interpreter is very slow. This is running a tiny Go hello world. It's kind of slow, and that's not a surprise. What is actually interesting is that the Chicory runtime with AOT on the with runtime Chicory with runtime AOT or precompile AOT are pretty much the same. There's not a big difference. And we get great performance on the Graal commercial version. We get good performance on Graal CE. We get better performance in Temurin and Temurin with GraalJIT. And the performance are pretty much the same regardless if you're using precompiled or runtime AOT. The interesting thing is that because Graal Wasm is meant to be optimized by GraalJIT, if you're running on plain Temurin without GraalJIT, you will get the same performance of an interpreter. Now, another quick example. This is, instead of just a hello world, this is running a demo that the GraalVM team developed using Rust, the Photon library for image processing. And in this case, the opposite is, so lowest is better here. So as you can see, the Chicory runtime AOT and the Chicory precompile AOT are still comparable. The Chicory interpreter obviously is terrible, as we all expect. We get a slightly better performance on Graal, but I mean, that's not the goal, to have good performance. The goal for the interpreter is to be correct. And surprisingly, or not, Graal Wasm, it's still getting worse performance on Temurin because the JIT compiler, the specialized JIT for Graal, is not available. Performance are better than Chicory interpreter, but not by a long gap. And this is just zooming in to show the Graal Wasm running on Graal and Temurin. When you actually zoom in, it's better than Chicory. But as I mentioned, there's space for improvement because we didn't really do any special work to make Chicory fast besides generating bytecode. The only special treatment that we do is we use unboxed values, and all these values are Java longs, that is 64-bit integers, which is essentially the same representation, at least at the boundary, that wazero uses. And conversions happen only at the boundaries. There are a few challenges. There are interesting open research problem in some ways, but one of the things that we encountered is that it's easy to, well, this is known, there's a limit to the size of a method on the JVM, which is 65K bytes. And currently, the way we're resolving this problem is falling back to interpretation or playing a little bit with the compiler flags for the Wasm module. So normally for our use cases, that is writing small plugins, this is not a big deal. But if you're just writing a plugin using Python, then you're bringing in the entire interpreter, and depending how you compile it and depending how how it's been optimized, it might, in general, the interpreter loop is kind of large, and it's not trivially splittable, at least if you try to split it using, from the point of view of Java bytecode. But a few talks today have shown how it's potentially feasible to spin off blocks. The problem essentially is that, as we mentioned, or as we know, the Java bytecode is unstructured, but Wasm bytecode is actually structured. So we could potentially extract blocks and make them their own methods, and that should probably solve our issue here. One last minute, I just wanted to tell you a little bit more about Android. As I mentioned, this already works in interpreted mode, and AOT also works, but the build time flavor. The build time flavor works because the Android toolchain works by translating ahead of time Java bytecode into Dalvik bytecode. And that just works, already works. So you can just bring whatever jar with Chicory precompiled modules from Wasm to Java bytecode, and obviously they will work. The challenge is if you want to do dynamic loading. And that's where we are also interested at Dylibso, because we want to be able to download these modules potentially dynamically and execute that code dynamically. Obviously, there's so we cannot reuse the same backend as it is, because Java bytecode cannot interpret it by the Android VM, the ART runtime. And so, because it's different kind of architecture, we have to roll our own, a different backend. And this is kind of a work in progress. It's showing some promises because of the 28K, about 28K spec tests that we're already passing on for the interpreter and on the JVM compiler. We already passed about 25K, so that's good. The other limitation is that in order to be able to do dynamic bytecode loading, you might need to use a recent framework on Android, but we can still fall back in interpreter mode in that case. And again, we can reuse a lot of the code, as I mentioned earlier. There are still challenges related to bytecode size again, but we will deal with them as we find them. This is still very early days, and this is really a work in progress. So that was all I had. Hopefully you liked the presentation. If you're interested in any other things that I've mentioned, just let us know. Let me know. There's mcp.run, xtism, wazero, and chicory.dev. And thank you.
Thank you. Does anyone have any questions?
I have a question regarding runtime loading of new modules. It's not, you said it's not possible to do it. So extension system, for example, you have an app, you create an app and you get extensions to load in. This is not possible on Android, most likely possible on desktop, but not on Android. Is this correct?
So the question is, load dynamically code. Is that right?
Is it possible to create plugin system? You download additional systems at runtime. For example, you have a framework, it's your app. You create extensions for this app and it's loaded on runtime later on. For example, you want specific sources, a new source, for example, or whatever, and it's running.
Right. So yeah, so on Android you can package plugins separately and create APKs for and distribute those binaries as traditional, so to speak, binaries for the platform. And yeah, you can write plugins that way. What we're trying to do with mcp.run is being able to fetch dynamically Wasm modules and load them on the fly. So that wouldn't work. What you could do, however, is pre-build the Wasm binaries, pre-translate these Wasm binaries, package them separately as APKs and provide them in some sort of service to the host, the main application. But yeah, it's a lot of work, but that would work, definitely.
So still APKs needs to be installed, basically. It's not possible to load at runtime later on.
I mean, you still have to install them. There's I'm not an expert of Android, to be fair, but I know that through interfacing with the marketplace, you're able to essentially let your user download them dynamically upon confirmation, go through the regular marketplace flow, and then they will be essentially available for loading dynamically. So in a certain way, it is possible to do it.
Okay, thank you very much.
Sure.
Since you've worked so much with Java bytecode and WebAssembly now, is there anything that you think Java gets right that WebAssembly does not?
I don't think there are things that Java bytecode gets right that WebAssembly does not. I think that Java has a long history, and thus it has a lot of features that are currently not available in Wasm. So one of the things that were mentioned earlier, like is instrumentation, and so dynamic bytecode manipulation and features like that are very useful for many reasons in the industry. But it's definitely, I think Wasm has the hindsight of 30 years of Java. So definitely there are things that it has learned from, and some things that might want to learn from Java. But it is definitely better in many ways.